The next layer of the sun above the photosphere is called the chromosphere. Chromo means color from the Greek. So this is a colored sphere. It was first observed, and anytime there's a solar eclipse, you'll see just as the moon just barely covers the sun, there's a very, very faint reddish ring around the sun. And so that ring is actually a layer of the sun itself that is just above the photosphere. That's always there. It's not just during an eclipse. It's always there, but it's normally much dim. Well, it always is much dimmer than the rest of the sun, and so normally you can't see it because the light, the photosphere, just overwhelms it. So during an eclipse, you can actually see it. It's glowing kind of a reddish color because it's due to hydrogen emissions. You remember in the lab when we set up the discharge tubes, the hydrogen gas was kind of a pinkish reddish color. And so that's the color of the chromosphere. When you zoom in on the edge of the chromosphere, you see it's got these little spikes on it. So there's these little spikes that are always shooting upwards away from the sun. And so up at the top of this picture, you see those little spikes. Those spikes are in fact called spicules. Ignore the big thing that looks like a big flame shooting out of the sun in this picture. We'll get to that later. But you see the spicules in here, down here, spewing upwards. They can go up for thousands and thousands of kilometers and then dissipate in a matter of just minutes. So something is actually energizing the gas in the sun and causing it to spew upwards like that. If you zoom in on the sun, and again, like the last picture, you saw the sun, you said, well, wait a minute, the moon's not blocking this. How are we seeing all this? Well, since we know it's giving off light just due to the gas of hydrogen, and hydrogen gives off certain colors that other gases don't, you can put a filter on the telescope that blocks out everything but that one color. And in that case, you can look at the chromosphere. This is called hydrogen alpha filter. And so here we see that the spicules are not just random. They tend to line up along the edge of the supergranules. So the question is, what clue does that tell us about this? Because something is causing these things to go spewing upwards. So what could possibly be doing that? Well, it's the supergranules. When the gases and the supergranules come together and go down, they actually squirt stuff upwards. And so that gives you the because you're adding energy to the gas to squirt it upwards, that makes it hotter. So while the surface of the sun is about 5,800 Kelvin, the chromosphere is actually hotter than that. Up near the top of the chromosphere, it's almost 25,000 Kelvin. But because it's so much thinner, it's not shining as bright. So energy has to be transferred from the photosphere to the chromosphere, and a lot of that is done mechanically through the squeezing of the gas. Turns out it's also done magnetically, and we'll get to that later. The other things you sometimes see in the chromosphere is you see some things sticking out like little arches or things hanging out away from the rest of the sun. Those are called prominences. If a prominence runs right across the middle of the sun, it kind of blocks your view, and we call that a filament. And so they look like little dark lines across the sun. And then plages, these plages right here, these are bright regions that are on the chromosphere. Now, interestingly enough, the plages tend to be sitting over sunspot groups, which are dark regions on the rest of the sun. Kind of wrapping up our little short presentation here about the chromosphere. You know how when you're teaching kids to draw the sun, you often have a circle here, and then you have the little jagged, spiky things like that. That's actually pretty close to the way the sun looks. Uh, Only the circle in the middle should be kind of a yellow-green color because that's the primary color of the sun, and the outer part should be spiky red things. So, all right. Thank you.